Good afternoon. I'd like to thank the program committee for inviting me. So I'm going to talk about reproducibility, essentially in computational science in neuroscience. Which ought to be an easy problem. I mean, compared to reproducibility in kind of biology, where there's lots of variability and differences between individuals. In principle, the code is code, and if you run it twice, it should give the same results every time, if only. In an open science mode, this is my slides are CC BY, so feel free to photograph, copy, they'll be available after the talk. So the first topic is reproducibility, and if you've ever tried to reproduce a published model, for example, in computational neuroscience, or even to understand a certain paper, then you might recognize some of these problems. But it's not just other people's work. I mean, it's also if you're just trying to reproduce your own work, maybe 6 months in the future, you sent the manuscript out to the reviewers, you get the reviews back, they want some changes to the figure, and then things start to go a bit wrong. So I thought I used the same parameters, but I'm getting different results. I can't remember which version of the code I used for figure 6. The new student wants to reuse that analysis I published 3 years ago, but he can't get the same results I got back then. And, it worked yesterday. Before going on to this, I just want to kind of talk about terminology a bit. So there's a range from reproducing your own code on the same machine, right the way through to a completely independent reproduction of your study, your computational study, based only on your materials and methods section, different computer, different software, and everything. Different words get used to this, so some people call this end replicability and this end reproducibility. Some people do it the other way around. So I'm going to use both terms more or less interchangeably, but I'm going to start off by talking kind of this end of the spectrum, and then when I get to reuse, I'm talking more about this end of things. So a lot of laughs when I talked about these problems that we see because we all recognize them. But what makes it hard? Why is it hard to replicate our own research? And so I think that boils down to three main problems. One is complexity. Our code is, we're modeling complex systems already. So the systems we're modeling are very complex, complicated, not complex in a dynamical system sense, but they're very complicated. And then our code and computation setups are also often complex. Writing software is challenging. Often there's very small details can have large effects. The second aspect is memory limitations. So we forget things. We hold things in our head one day, and then we forget some of the details as time goes on. And often these things are critical to the results, but we don't remember that they're critical at the time. And then the final problem is just things decay. So computing environments change, versions of dependencies change, your computer changes, and this makes it very hard to reproduce our results. Okay, so what can we do about it? So I think for the complexity problem, then, software engineering has tackled this, been tackling this problem for many years, and they've developed some good tools. So I think one, you should try to write robust code, where robust means it's kind of insensitive to the precise details of the code or of the environment. So if you try to make it faster, can you just change one part of the code, or do you have to change everything everywhere in the code? If you upgrade your operating system, does your code still run? Do you get the same results? If it's robust, it will. If it's not robust, which unfortunately I think is the case for much scientific code, then you might not get the same results. And so I'm not going to go into detail on this. There are lots of books on this topic, lots of things you can do. I think probably the key thing, especially in a scientific concept, is the last one, that you should design your code to be easily understood by other people, where other people can be yourself in 6 months' time. So how do you do this? Lots of things you can do. Write lots of comments, write documentation. And then finally, this is my favorite one, is don't be too clever. So this Brian Kernighan is one of the guys who developed the C programming language and the Unix operating system. And he said that debugging is twice as hard as writing the code in the first place. So if you write very clever code, you're by definition not clever enough to understand it, to debug it. So the next thing you can do to write robust code is to test it. So how confident are you that what your code actually does is what you think it's doing? And what tends to happen in science is that we use very informal testing methods. So that looks about right. The results kind of what I expect to see. I'll print the graph out and I'll measure the points off the graph and compare it to the values I calculate it should be by hand. It looks more or less the same. I think this is still very widespread, but really we need to get past this and again adopt practices from software engineering. So for all the tests you were performing manually before, you should write a script which does that same test. This gives you confidence your code is doing what you think it's doing, and it actually frees you up. It means you can make more wide-ranging changes to your code without worrying you're going to break something. If you do break something, you know about it straight away. And this is worth the time. I mean, if you already perform this kind of manual informal testing, then the time you spent writing the automated tests will probably be paid back the first or second time you run the automated suite of tests, just because doing these tests manually is often so time-consuming. And you'll also make faster progress. So on the issue of memory limitations, I think the only real solution is to record everything, right? Get everything recorded. And then how do we do this? I mean, in science, the traditional approach is that you write everything down by hand in a lab notebook. But when it comes to computational experiments, there's just so much stuff you have to write down. So what code am I running? What version, what parameters, what input data, what output data do I get? Who ran the simulation, on which machine? What was the architecture of that machine? What was the version of the operating system? There's so much information you need to record to reliably reproduce an experiment. So if I was giving this talk, let's see, 3 years ago, 5 years ago, at this point I would have talked a lot about version control. I guess I don't need to do that anymore. Just information, so who here writes code and does not use a version control system? Yeah, okay, good. So, so I can pretty much skip that. I mean, there are lots of tools out there that we can use. I think that's actually in itself been an amazing change we've seen in the field over the past 5 years. Fernando Perez this morning said that using Git is like it's like using it's a toothbrush for science. So it's something you should be using every day, and that's a great analogy. Okay, so we're using Git. So we've now ticked one of these things on this list of things we have to keep track of. We know which version of our code that we wrote we were using. But that's not really enough. There's all this other stuff that you really need to record as well. And so recording all this stuff comes in the general topic of provenance, so keeping track of where does your results come from. And there are 3 general approaches that have been taken. The first is literate programming. This was first, I think, invented by Donald Knuth, who's the guy behind the TeX typesetting system. And the more modern version of this is IPython Jupyter notebooks, where essentially you type your code in one place and you see the results in line right next to the results. This takes care of keeping track of what code gave what results. Yeah, or does it? Because the problem is that what you have there is very much the stuff that's above the surface on the iceberg, and all the stuff under the surface in terms of precisely what versions of libraries you use, what compilation options you use, what operating system. I mean, all of these things, as we've seen, can have a major impact on your results. And so how do we capture all this stuff under the surface? So a second approach is to use a kind of pre-built system which takes care of all these things for you. So there are a lot of these visual workflow systems. Taverna is one example, but there are many others, where you have a kind of a computing environment which is predefined and everything's known about it, and then you kind of programming it in a visual workflow type of way. So this certainly does the job, and this will capture all of this information that you need to have behind the scenes. You don't have to worry about it. The main problem is that you have to really change. If you're not working this way already, you have to change your way of working to adapt to this visual workflow approach. And so I think systems like Galaxy, which have seen a lot of uptake in bioinformatics, but otherwise it hasn't been very widely, I think, uptaken in computational neuroscience, certainly. So the third option is environment capture. And so here the idea is that we just capture all the details automatically. We capture all the details of the code, the data, the environment, so that we can then reproduce it at a later date. And the nice thing about this is you can just adapt and extend your existing workflow rather than completely replace it with something else. And so looking at the possibilities in this space, there are two main axes. Firstly, whether we capture our environment as a binary format, or whether we actually just store the metadata that you'd need to recreate the environment later. The other axis is time. So do you preemptively define your environment and always use that environment, or you can capture the environment at runtime to get the exact environment you definitely used at the time you ran the computation. And there are tools in all of these spaces. So there are many ways now to create these predefined environments. The idea that you do all your research in a virtual machine or a software container using something like VirtualBox or Docker. Ideally, you should script the creation of this environment, which is what Dockerfiles do. You can also use other tools like Puppet, for example. And so when other scientists want to reuse your results, you just send them the VM and they rerun the simulation, or they can even use something like MyBinder, which again Fernando Perez talked about this morning, to just automatically launch and rerun the same environment in the cloud. So this is great, and so kind of Docker sits in both of these quadrants. So this is kind of the binary artifact that you've captured, but also you have the kind of Dockerfile used to create the environment. So you also have some of the metadata that you need for this. One disadvantage of this preemptive capture is that sometimes the environment has changed a bit. You've done something to the environment between the time you created it and the time you ran the experiment. So the advantage of, I'm going to skip this because I guess everyone, who here hasn't used Docker? I'll very quickly go through this. So for those who don't know about Docker, so it's a lightweight alternative to virtual machines. It creates a portable, isolated Linux environment that can run essentially any Linux host, also on OS X and Windows. And you can download pre-built environments, or you can build your own environment. So here's an example. If you want to do simulations with Nest, then you start with a kind of a base package. In this case, we're using the Neurodebian package. You install some more Debian packages that you need for Nest. You create your Python environment, download and build Nest. And so then now all you have to do every time you want to use Nest is not on a new machine, is not redo all of this. You just take your, you build your environment, your Docker image, and then you can run it anywhere you want. And you have this environment where you can immediately start to use Nest every time. And so using on a new machine is as simple as just copying the Docker image and getting going with a single command. You can also make changes. You can commit the changes and save that particular environment and use that version later. You can also take pre-built environments. So here I'm pulling a pre-built environment from the web, running it, and in this case it's one you can actually SSH into to get multiple clients accessing the same container. And so in a very few lines, you can have a reproducible environment with all the tools you need to do your simulations. So the nice things about virtual machines in Docker, they're very simple and they're pretty robust, certainly in the short term. And the nice thing is they capture everything in your environment. Lots of disadvantages. So VM images are very large. Docker is a bit smaller, but still about a gigabyte each time. And the risk is that you kind of end up having not robust code. So it runs in this Docker image, but it doesn't run anywhere else because you're always using the same environment. So this is a disadvantage. You also can't index, search, or analyze the provenance information that's kind of trapped inside this container very, very easily. So yeah, this is a disadvantage. So as I say, you can change it after you've created it. And so for that, you really want to capture the environment also at runtime, so you know exactly at the time you ran this computation what the environment was. So there are various tools for that. One nice one is called CDE. Essentially, anytime you run whatever you run on the command line, you just prepend CDE, and then it uses the Linux strace operating system call to automatically see all the files, libraries, etc. that get opened. It takes copies of them and packages them up. And then you have a nice little small package, so not the size of an entire operating system, that you can send to people. They can run it on their machine using CDE, and it will use the libraries and all the code from there, from the package, rather than from your own host operating system. There's a similar tool called reprozip from NYU. And so this approach is kind of nice. It's more lightweight than the full VM, much smaller files. doesn't have the performance penalty of using a virtual machine, and again, it requires minimal changes to your workflow. It has the same disadvantage that you might get end up with unrobust code because you're tied to a particular configuration that works, and again, you can't index, search, or analyze the information. So the final option is runtime metadata capture, runtime metadata capture. So rather than capture the entire kind of binary environment, you capture the information you need to rebuild the environment. And again, there are lots of tools in this space. And the advantages are that once you have that, then you can index, search, and analyze the provenance information, which you can't do with the purely binary approaches. Disadvantage, you might not capture all the context, and you don't have this plug and play. It gives you the information you'd need to recreate it, but it doesn't recreate the environment for you. So there's a tool developed originally in my team, which is now has a wider community called Sumatra. The idea is that you just prepend, you can configure it that you prepend your command line with SMT, and this will run your simulation as normal, but it will do various things. It will go into your code, it will analyze your code, it will find all the dependencies that you use. This works for Python, it works for R, it works for other languages which have a plugin defined, and it'll try to find all the libraries and try to find all the version information from those libraries. It'll similarly track the machine information, the processors, all this kind of thing, and it'll put all this stuff into a database, so you can see a full history of your computational project. You can see the repository that was used, the Python version, the input data, all the output data, the dependencies with the versions where the system can find them, the standard error, the platform information, and so on. One nice thing you can do once you have this metadata in a database is, for example, if you're using LaTeX, this is a Sumatra package for LaTeX, so you can include a figure from your database with its hash, so you know it really is exactly this figure. And when you build this, it'll give you a PDF where the figure is also a hyperlink to the database, which shows you exactly how this figure was created, what the exact environment was that you used to create this figure. There are other tools like Sumatra, Recipe, NoWorkflow, and there are other online databases. There's something called Cloud of Reproducible Results, which supports various of these tools and lets you visualize the full kind of provenance history of your computational project online. Yeah, so those are the different possibilities. What I might recommend is, I guess I'm in North America, I should say belt and suspenders. Yeah, use both. So use a predefined environment, use a Docker container or a VM, but also use something like Sumatra to capture the runtime, and that any changes you've made since you created the VM are also captured. The final thing is entropy. The final problem is entropy. But I think in general, if you've followed the advice for the first two problems, the things which you need to do to solve the complexity problem and the memory problem in terms of planning for reproducibility from the start by creating a virtual environment, running different environments, writing tests, recording dependencies, then you've also pretty much solved the entropy problem as well. So moving on from your research to other people's research, why is it hard to reproduce other people's research? So in addition, of course, to the same problems that you have for your own research, there are additional problems. So often code and data still are not shared. If they are shared, it's not always easy to find where it's been shared. And then, of course, there's missing information that you need, it's things the authors assumed you would know, or they forgot they hadn't written down into the materials and methods. Kind of a worse version of the dependency problem that you might not have access even to all of the code and libraries that they used in their study. So what can we do about these problems? These ones are more difficult. There's only a limited amount you can do individually. But one thing, in terms of code and data, as a reviewer at least, when we review, we can insist on code and data being made available. And in terms of missing information, well, INCF, we can promote metadata standards so that more of this information is automatically captured as part of the publication process and not just left to the kind of whims of the author as to whether they remember to write it in the materials and methods section. And we can also, when we do manage to reproduce a study, we should try to publish it so that other people can benefit from that work. So in terms of reviewing articles, so I'd like to perhaps advertise this open source for neuroscience open letter. So 203 people so far have signed, and if you sign, then you're pledging that not only will you release your own code, all the code that's needed to reproduce your results when you publish yourself, but you'll also, when you are serving as a peer reviewer, you will also always ask the authors, or even require the authors to make their code and data available. So far we have 203 signatories. This was a project which was started by Giorgio Ascoli and Parry Gleason, Angus Silver, and myself. And so hopefully, if you all take note of this URL, then by the end of this, we can get this up to 300 by the end of the afternoon, maybe. So yes, but please, when you're reviewing, think about future reproducibility of this work. And then another nice thing in terms of when you do reproduce a study, which is something we quite often ask students to do, that a good starting point is to take an existing paper and try to reproduce it, and then build on it. Then often that was work you did, but you couldn't really publish it. Whereas now there is a venue for this. So Rescience is a peer-reviewed journal which publishes independent replications. Yeah, this is not rerunning people's original own code. It's actually writing a new implementation of this model, of this data analysis, which gives the same results, and checking that it gives the same results. And in fact, this has been taken up quite enthusiastically in computational neuroscience. A lot of the papers so far published in this journal are from computational neuroscience. It's also on GitHub, so submitting is as simple as doing a pull request on GitHub, so that's kind of a nice feature as well. So yeah, so if you or your students do reproduce previous studies, please think about publishing them in a venue such as this. So I've talked about reproducibility. Next issue is beyond that is reuse. So reproducibility, okay, that means you can recreate your own results, but if you really want this to be used and taken up by the field, so going from reproducible to reusable is lots of polishing, basically. So what's good enough, and I think in terms of what's good enough to put out there for a scientific study, it doesn't really matter if it's highly polished, as long as it worked for you. That's good enough. It should be published. But if you want other people to reuse it, it has to be a bit more robust. It should be easy to install. It needs good documentation. I liked Russ Poldrack's comment from the first day that his goal is that no one should ever have to talk to him about the stuff he publishes. So this should be the goal, because you can't solve everyone's problems individually. So if you add good documentation, they won't have to talk to you about it. But equally, people, when they start using your code, they're going to find the inevitable bugs, and so you're going to have to deal with those bugs that people find. And this is an additional burden when you go from just reproducible to actually reusable. Why is reuse important? Well, it's not always. So not all code, not all models do need to be reused. But I mean, this is science, and so to a certain degree, I mean, that's part of what we do is building on work which has gone before. I think for the field, it's extremely important. I think it increases the efficiency of the field to build on existing models and code, and not just on existing ideas. It reduces the time to the next advance in the field. For the individual, I think it has very positive effects. It magnifies the impact of your work. You tend to get more citations, for example, if you publish reusable. If people can reuse your code and actually build on it. It makes your science better in that people find bugs and edge cases which you didn't consider, so you have to make corrections and you improve and refine your work. And finally, it supports long-term reproducibility. So if something is reusable, it means it's getting run more than just once, and so it will be in the long term more likely to be reproducible in the long-term future. But so why is it difficult? So for models, models are often tied to implementations and simulators. What you do when you get bug fixes and improvements, you can't really publish an erratum for every single bug report that you might get. That way doesn't really work in the modern world. And there's a problem of forking and fragmentation. So you might have different labs take your work and then take your model in different directions, for example. And so then is there any way you can kind of bring these back together into a kind of combined model which has the best of both worlds? So there's a risk of fragmentation in the use of the code. Why is reuse difficult in terms of code? So in general, so for data analysis code, for example, largely it's the maintenance burden that once it's reusable, then you might want to, you feel obliged to somehow accept contributions, but those might break things. The people who worked on it probably might well move on, so it's kind of hard, the maintaining things in this environment where there's continuous movement is very difficult. And then you have all these edge cases and other people's use cases which kind of add to this burden of maintaining code to make it reusable. And of course, for both cases, there's kind of lack of academic recognition for all this polishing that you do to make your code reusable. So what can we do about it? So for models, the first problem that models are tied to implementations and tied to particular simulators. Well, there are things we can do about this now. There are tools like Pine and NeuroML and 9ML, and a lot of my other talks are about that, so I won't talk about it now. In terms of dealing with bug fixes and improvements, so I think rather than publishing the erratum every time you have a bug fix, then if everything's in version control, it's in GitHub, it's in Bitbucket, it's in open source Brain, then you can have multiple versions of your code, and people can go to your code and get the latest version with all the bug fixes, and not necessarily just the version which you published at the time, the version that was there at the time the paper was published. In terms of forking and fragmentation, I think the solution is somehow the same as for forking and fragmentation with code. There, I think part of the solution is automated tests and continuous integration. So the equivalent of automated tests for models are validation tests. And so we heard from Sharon Crook yesterday about the SciUnit framework. And so there are tools from my group in the Human Brain Project, which let you generate large libraries of validation tests. And so you can take different models. There are more from Sharon's lab and the SciDash project, but you can take different models and you can take different tests, and then you can compare, okay, I have these two models which have been forked from the original version, and now I can use the validation test to compare them. And so if I then merge them together, do I get better results in terms of validation than the original separate models or not? So there are things we can do. From models to code, so for the maintenance burden, as I just said, in terms of accepting contributions, if you have test suites, then you have all these continuous integration tools, and they hugely reduce the burden of accepting these contributions because you don't worry about them breaking things so much. This also solves the edge cases problem. People can come and add their own edge cases to your code, and as long as they have unit tests for it and your other unit tests don't break, then it's okay to accept it. Other people's use cases, yeah, I mean, avoid if at all possible. It's just, I mean, it's nice to accept them, but it's far better to say, okay, please, you do the work, and I'll merge it when all the tests pass. Otherwise, I mean, from experience, it can be a big time sink. And I think the solution to the fact that people move on, and I guess that this is also true in open source software more generally, and the solution is community building. Of course, this is a problem in itself, but if we take as an example the Neo package, which I developed, so this has been quite successful. It's gained a fairly wide number of contributors to the tool, 44 over time. And if we look at the kind of commits on GitHub over time, we can see there have been a couple of kind of like steady. So I think this is me. And another one is another, like someone who has a permanent, who has tenure. But otherwise, all the contributions are kind of like rather limited in time. So people who were working on the project at a certain time during their PhD, they had a need for the project, they needed to improve it, so they contributed something, and then they moved into something else. And I think a similar trend you can see with NumPy, for example, where there's a certain number of contributors who contribute a lot at certain periods of time. This guy presumably was back in time, but others it's very short-term contributions, a short defined period of time, and they move on, and that's okay because it's a community, and so overall the activity stays steady over time. But it's difficult. Time building these communities is difficult, so it kind of worked for Neo. It hasn't worked for some of the other software projects I've been involved with. You have to set up mailing lists, you have to set a website, you have to run meetings and workshops. You have to be responsive to people who want to make improvements or report bugs or submit pull requests, and you have the same old problem of other people's use cases. It adds to the difficulty. And so while this is certainly a worthwhile road in many cases, if your tool is really standalone and novel and really worth being reused, then it is definitely a worthwhile investment. However, sometimes you can avoid it. So in general, it's better to contribute code from the existing library rather than roll your own from scratch. So an example here is Elephant, which has been designed. This is a library for analysis of neurophysiology data, but it's designed as exactly this kind of like central place where people who develop new data analysis methods, which happens all the time in neuroscience. There are so many, almost every PhD and postdoc in neuroscience that will develop some novel analysis method for their data, and often these methods, maybe at the best case, they get published as a standalone package that no one can find. Worst case, they never get published at all. And so Elephant is designed as a place where people can contribute this code and have it being reused without the maintenance burden. So the maintenance burden is taken on by the community as a whole, and it means that your code can actually get reused without you having to do all the work. Yeah, and in terms of the lack of academic recognition, this is a hard problem. But there are some things we can do. I mean, so I think Zenodo is very nice now in that you can kind of get a DOI for a specific version of a software tool, for example. And that's me. So just to put up a summary of the recommendations to maximize reuse and reproducibility. And I'm happy to take questions. Thank you.
Thanks for the great talk. Does anybody have questions?
Have you spoke with Gael? On a more serious note, regarding your comment about reviewing papers and requiring code and data, there is another initiative called PRRO, basically, I don't know what it stands for. It's quite a long-going thing where basically people pledge they will require code and data, and it's across many different fields. And a lot of people sign it. I just want to share my experience of doing that as well. So I signed it as well, and I started, when I got a review request, I would send back to the editor, well, I would like you to ask the authors to say where the code is and where the data is, and most of the time, the editors just ignore me. And sometimes they write back saying, this is not the policy of our journal. And it's true, it's not. But there's a solution, which I adopted a while ago. It's a service called Academic Karma, which has the service called Reviewer Agreement. So whenever you get a request to review a paper, you figure out, you get the paper, you get the authors, and before you actually accept the review from whatever journal it is, use this service to anonymously, anonymously contact the authors and tell them, hey, I am willing to review your paper. You can decide whether you're going to sign it or not, whether you're going to publish this review or not. So you can actually give something in return to the authors. You can say, well, I'll review it in 2 weeks, and I'm going to sign it, I'm going to make it public, so you can reuse that review for other submissions. But I would like you to publish a preprint, put the code online, put code online. And those are all options. You choose which of these things you care about. And you make that agreement with the authors before you actually accept the review. So you can verify these things, you can see the preprint, and et cetera, et cetera. So I found it much more effective than actually arguing with the authors or editors post hoc, because there's a ton of excuses such as, well, my code is too messy and whatnot. So just wanted to share that sort of little trick, how to make a world a better place.
Okay, thanks, Chris.
I'll talk to Gael.
Hi, Andrew. Thank you. Wonderful talk. One question that I have is that I know that pulling in the binaries is one thing that is very practical. but at a certain point, that pollutes your provenance chain, where if you don't know what version of GCC somebody compiled that binary with, you're going to have bugs that you don't know exist until they show up, and then you're not necessarily going to be able to debug them. Are there ways around that with the tools that exist, or do we have to go to a source, bootstrap everything from source if we really want to think about what the end game for this would look like?
So wouldn't this idea of both capturing the binary environment and the metadata solve that problem? That you can always go into the actual binary environment and find out the information that's missing.
If I am running a Debian distribution, I don't know whether it's possible to know directly, for example, which version of GCC those binaries were compiled with. There might be ways that you could reconstruct it, but it's not something that would, I imagine, show up immediately in the database.
Yeah, I would say that it's certainly a problem. I mean, so in Sumatra, for example, it can't always find a version number, but the idea is that more information is better than less information. So, yeah.
Thanks for the great talk. My comment is this talk is great because it gave this sort of huge overview of all the different things that people could and should be doing, and it makes clear that there are so many of them that it's sometimes people just forget because there's so many other things going on, and so it's I think it's important for like these slides like these to be made into really accessible sort of like pamphlets or things that like provide for helpful reminders and things, because sometimes, well, it's I think there's a lot of consensus that all these things would be nice to be done. People need help to remember and to have like clear guidelines and clear like methodologies to do those things, because it can't be overlooked that people can just forget in the stream of work.
Yeah, yes. I guess I should probably write this up somewhere. Maybe make a YouTube video.
Right. So while we have technically made it into the coffee break, are there any questions for the, grander set of speakers that we had in the session? If not, then I'd say we thank all the speakers again and enjoy the coffee.